Have you ever stopped to think, really think, about what happens behind the scenes when you encrypt something? Your data. We put so much trust in, the math, these complex algorithms. We figure, okay, our secrets are safe, locked away. But what if the very act of locking them away, the encryption process itself, what if a power the device uses, or maybe tiny electromagnetic waves it gives off, could actually betray you? Today, we're doing a deep dive into this fascinating and honestly, yeah, a little bit unnerving world of side channel analysis, SCA attacks. Now, these aren't your standard hacking attempts, not trying to guess your password or find a software bug. No, these are sneakier. They exploit the physical leakages, you could say, from the devices themselves. They can pull out cryptographic keys even when the encryption math is like perfect, theoretically unbreakable. It's not about bad math, it's about unintended physics.
It's a really interesting paradox, isn't it?
Yeah.
You take something like AES 256, mathematically, incredibly strong. Trying to brute force it is, well, it's just not feasible with current tech. But, and this is the crucial part, how you implement that algorithm on a physical chip, that can inadvertently leak vital information. Think about it. Every single calculation, every tiny switch flipping inside that microchip, it has a physical effect. A tiny power surge, a faint EM pulse. It's like a whisper. And a clever attacker, well, they might be listening. So our mission today in this deep dive is to really unpack some groundbreaking research. It's found a really ingenious way to virtually shut down these physical vulnerabilities. We're talking about making our digital secrets safer than ever, really securing them right down at the hardware level. We'll be exploring this cutting-edge solution. It combines a few things, a digital-friendly current source and something called a ring oscillator, or RO bleed-based integrated local feedback, with global switch mode control. It all comes together to create an SCA-resilient AES 256 engine. It's quite a leap forward.
And the key thing here, right, isn't just that it works in a lab, it's that it's synthesizable.
Exactly. That's a huge differentiator.
What does that mean, synthesizable, for us?
It means the design can be easily generated, checked, and scaled up using standard digital design tools, the kind engineers use every day.
Okay.
So you can mass produce it. You can easily integrate it into all sorts of devices, your phone, critical infrastructure, you name it. It adapts to new chip technologies without a massive redesign effort every time.
Unlike older methods that needed special analog parts.
Precisely. Analog components are tricky. They don't scale easily. This is all digital friendly.
So it's a practical, buildable way to shield AES 256 from these stealthy side channel attacks. Okay, get ready for some aha moments because we're going to explore how brilliant minds are fighting these invisible threats, trying to keep our digital world safe, right down to the silicon. All right, let's unpack this a bit more. Side channel attacks, what are they really? Imagine you're trying to figure out what's going on inside a locked room. You can't see in, the lock's perfect, you can't pick it, but maybe you can hear things. Footsteps, the lock turning, papers rustling, maybe a machine humming. Side channel analysis, SCA, it works on a very similar idea. It's not about breaking the encryption algorithm itself, the math. It's about carefully watching the physical side effects when that algorithm runs on a device. These tiny effects, things you wouldn't normally notice, they become clues for an attacker. And this research, like a lot of work in this field, it really focuses on two main things: power consumption and electromagnetic signals, EM signals. Every time a circuit does something, it draws power, right? Current. And at the same time, it emits these tiny electromagnetic waves. The key thing for an attacker is that these signals, they aren't just random noise. No, they're actually linked, correlated with the data being processed. And crucially, with the secret cryptographic keys being used, think of it like a digital footprint. Every single calculation a device makes leaves this unique, tiny signature in its power use or its EM emissions. A sophisticated attacker, someone with the right gear and the right analysis tools, can study these tiny footprints, and they can actually piece together the secret data, like the key to your encrypted stuff.
It's like reading what someone wrote in a sealed envelope just by analyzing the pen pressure.
Exactly. You don't see the message directly, but you figure it out from the physical process.
Which brings us to a really critical question. If an algorithm, say AES 256, is mathematically solid, why pour so much effort into stopping these physical attacks?
Well, our view is, knowledge is only truly useful when it's understood. And SCA attacks really drive home the point that even with ironclad math, a tiny physical weakness can just blow the whole thing wide open. The danger is huge. It's far-reaching. These attacks can compromise incredibly sensitive stuff. Your bank details, online chats, even national security secrets. And the attacker doesn't need to hack your network or find a software bug. They just need physical access or proximity to monitor the device's power line or its EM signals.
So they bypass a lot of the usual defenses.
Completely. It makes them a silent, almost invisible threat. Hits right at the trust we place in our hardware. The implications are, frankly, enormous. Okay, this is where it gets really interesting for me. How do you actually measure how secure something is against these attacks? Is there like a rating system?
There is, yeah. We use a metric called minimum traces to disclosure, MTD.
MTD. Right. Break that down.
Sure. MTD is basically the smallest number of encryption operations or traces of power or EM signals that an attacker needs to watch to successfully figure out the secret key.
Okay, so fewer traces means it's easier to break.
Exactly. A low MTD means it's relatively easy, doesn't take many observations, the attack is quick, potentially cheap. A high MTD, on the other hand, means it's incredibly difficult. You might need billions of traces.
Billions.
Billions, which makes the attack practically impossible within a reasonable time or budget.
So it's the difficulty rating for picking that digital lock just by listening to its clicks. Low MTD, loud clicks. High MTD, it's silent.
That's a good way to put it. And MTD is so crucial because this research gives us a really stark baseline. An unprotected AES-256 implementation, the kind that might be in, well, countless devices right now, it can be broken with a shockingly low number of traces.
How low we're talking?
For power analysis, just 7,000 traces. 7,000.
Wow, that sounds fast.
It is. And for electromagnetic traces, it's around 9,000. Think about a modern device doing thousands of encryptions a second. An attacker could potentially get your key in seconds, maybe minutes. It's a very real, very immediate threat. And this leads into the broader context, right? Researchers have known about this threat for years and have been developing countermeasures.
What kind of things did they try before?
Well, early ideas included things like current equalizers, trying to smooth out the power draw, also series low dropout regulators, LDOs, and integrated voltage regulators, IVRs. The goal was generally to give the crypto core a cleaner, more stable power supply,
Right.
which indirectly reduces those signal variations attackers look for.
Did they work?
They offered some protection, yeah. They pushed MTDs up maybe to around 10 million traces in some cases.
Okay, 10 million is way better than 7,000.
It is, but you have to remember, even 10 million might still be feasible for a really determined attacker. An LDO, for instance, it might stabilize the overall voltage, but maybe not react fast enough to smooth out the really quick, tiny, data-dependent current spikes during the AES rounds. Those are the ones that really leak the key info. Plus, these older solutions often had pretty big drawbacks that limited how widely they could be used. A lot of them relied heavily on analog components.
Right, you mentioned analog is tricky.
Very tricky. Effective, sometimes, but hard to scale. Every time chip makers move to a new process, like from 65 nanometers down to 45, you need a major, expensive manual redesign for the analog parts.
Slows things down, costs more.
Exactly. And even if some solutions were more digital, they often only gave moderate protection. Not the kind of Fort Knox security you need for really critical data. So the big challenge has always been finding solutions that are both super effective and easy to implement. Synthesizable, scalable across new technologies. Robust security without breaking the bank or needing a total redesign for every new chip.
And that's the gap this new research is aiming to fill.
Precisely.
Okay, so let's unpack the core idea, the breakthrough. If the problem is the signature, these power and EM wiggles leaking information, then the solution seems logical. You have to attenuate it, flatten it out. It's like trying to walk across that dusty floor without leaving footprints. You try to be super light, maybe float, or wear special shoes so there's no clear print left. Or back to the locked room, make the sound coming out just a constant steady hum. Doesn't matter what's happening inside, the sound outside is always the same. That's the basic idea, right? Make the physical signs of encryption so flat, so uniform, that there's no information left to grab.
Exactly. That's the core concept. And previous work, some papers referenced as 4 and 6 in the research, they really showed the potential here. By focusing on making the supply current to the crypto core almost perfectly constant, they achieved incredibly high protection. MTDs over 1 billion.
1 billion traces.
Yeah, a huge theoretical success. It proved the power of this signature attenuation approach. But, as we just discussed, the challenge was making it practical, scalable.
Because they relied on analog stuff.
Many did, yes. Complex analog circuits. Which brings us to what's really revolutionary here. It's this leap from those older, often analog-heavy methods to a solution that is fully synthesizable.
We keep coming back to that word, synthesizable. Remind us why it's so critical in chip design.
because it means the design can be automatically generated, verified, and scaled using standard digital design tools, like software compilation, but for hardware. This is absolute vital for modern chip making. It allows for fast prototyping, mass production, easy adaptation to new chip technologies, all without needing teams of engineers doing manual redesigns every time.
Which you need for analog.
Which you often need for analog, yes. Analog parts are finicky, hard to port between tech nodes, costly to tune. Synthesizable means digital, scalable, cost-effective. And the trade-off used to be really stark. Earlier methods with super high protection, like the one in reference 4, they used things like analog-biased cascode current sources, analog bleed paths, great protection but hard to scale. On the flip side, you had designs like in 2 and 5. They were synthesizable, which was good, but using just a single countermeasure, they only got moderate protection, maybe 10 million MTD.
So high protection but hard to scale, or scalable but only okay protection. That was the dilemma.
That was the dilemma until now. This new approach, the Digital Signature Attenuation Circuit, or DSAC, it aims to break that trade-off. It takes the high protection principle of signature attenuation, but makes it entirely digital, fully synthesizable. And the goal wasn't just a small improvement. They were aiming for a huge jump in MTD. From that 10 million baseline for single synthesizable techniques up to 250 million.
Wow, a 25 times improvement in a synthesizable package.
Exactly. That's a massive leap for practical, scalable hardware security. It means getting top-tier protection and the benefits of digital design. Best of both worlds.
So how did they prove this worked? How did they test it?
They implemented the AES-256 engine on a real chip, a custom 65-nanometer CMOS integrated circuit, an IC. And very cleverly, they designed it with 3 different modes you could configure, so they could do direct, really clean comparison.
That's one.
Mode 1 was the baseline, just the standard, unprotected AES-256, the kind you might find everywhere. This showed them exactly how vulnerable it normally is, a benchmark.
Okay. Mode 2?
Mode 2 added the first layer of protection. AES-256 protected only by the DSE, just the core innovation on its own. This let them measure its standalone effectiveness.
Makes sense. And Mode 3?
Mode 3 was the full package, a layered defense. Here, they combine the DSA with a second, also synthesizable technique, something called time-varying transfer function, or a TVTF.
DSAC plus TVTF.
Right. This mode was designed to show the combined power, the synergy, when you stack these advanced, digital-friendly countermeasures.
So unprotected, DSA alone, and DSAC plus this PVTF thing, that sounds like a really thorough test plan.
It provides very strong evidence for how well DSE works, both by itself and when combined. Right. Let's get into the nuts and bolts of the DSE itself. The digital-friendly signature attenuation circuit. It's really an elegant piece of engineering integrating several digital parts, and that's key to why it's synthesizable and works so well. Primarily, there are 4 main components working together, all aiming to flatten out those power and EM signatures from the AES core. And looking bigger picture, it really represents this important shift away from complex, sometimes fragile analog controls towards more robust, predictable, scalable digital solutions, better suited for modern chip design.
Okay, component 1. You mentioned a current source.
Yes, the synthesizable current source. This is the heart of it. Remember, the goal is a constant current supply no matter what the AES is doing, because any fluctuation leaks information.
And this one is digital, unlike the older analog ones.
Exactly. Instead of complex analog biasing, this one is built from 32 digitally tunable stacked PMOS slices.
PMOS slices.
PMOS transistors, a type of semiconductor switch. Stacked means arranged in layers. And digitally tunable means you can turn slices on or off digitally to precisely control the current output. Very fine-grained control.
How does it control itself? Bias itself?
That's the clever part. It uses a self-biased inverter to generate the needed voltage and pass gates to control the biasing. It's an ingenious all-digital setup. It completely gets rid of the need for those tricky, hard-to-scale analog blocks. Makes the whole current source fully synthesizable. Elegant, really.
And it does more than just provide current. You mentioned suppression.
Right. It provides high output impedance. Think of it like a strong buffer or filter. Even if there are small voltage dips, maybe 20, 30 millivolts, right at the AES engine itself, this current source stops those fluctuations from getting out to the main power pin where an attacker could measure them.
Like a shock absorber for the power line.
A very good analogy, yes. It dampens the internal noise before it escapes. But that leads to the next question. Even with a really steady main current, could some tiny key-dependent variations still sneak through? Almost imperceptible ones.
Ah, okay, so there's another layer.
Yes, that's where component 2 comes in. The RO bleed-based local negative feedback, LNFB. This acts like a super fine-tuning mechanism.
RO bleed, what's that?
The DSAC uses multiple parallel ring oscillators, ROs. Think of them as simple digital oscillators. And here, they act as a precisely controlled bleed path.
Like a tiny leak valve.
Exactly like that. These ROs divert a very small, carefully calculated amount of excess current away from the AES core, this diverted bleed current. It's meticulously matched to the tiny difference between the current the main source is supplying and the actual average current the AES is drawing at that moment.
So it cancels out the tiny variations.
Precisely. By adjusting this bleed current on the fly, the LNFB effectively masks those critical, tiny, key-dependent variations in the cryptocurrent that would otherwise leak the secret. It's like an incredibly sensitive balancer, siphoning off just enough excess current to keep the total draw perfectly flat, silencing even the faintest whispers.
And you control how much it bleeds.
Digitally, yes.
Yeah.
You just tune how many of these parallel RO bleed stages are active. It's a very precise, all-digital balancing act.
Okay, so we have the main constant current and this local feedback handling tiny variations. What else? You mentioned stability, environmental changes.
Right. That's component 3, the global negative feedback, GNFB. Switched mode control, SMC loop. It's just like the overall supervisor, ensuring stability against bigger changes.
And this is digital too.
Fully digital. It uses the same ring oscillators from the LNFB. Their frequency naturally changes based on the voltage across the AES core, let's call it VAES. This frequency is then measured, counted, by fully digital switched mode control logic, SMC logic.
Okay.
And here's a really clever bit. The SMC uses a deadband.
A deadband.
Yeah, a predefined safe operating range for that VAES voltage between an upper and lower limit. And crucially, as long as VAES stays within that safe range, the global feedback loop actually switches off. It disengages.
Why disengage? Wouldn't you want it always active?
Because you want the main PMOS current source to focus purely on attenuation, on flattening the signature. You don't want the global loop constantly fiddling and potentially adding noise if everything's already stable.
Okay. Let the main attenuator do its job undisturbed.
Exactly. But if VAES drifts outside that deadband, maybe because of temperature changes, voltage fluctuations on the main supply, manufacturing variations, we call that PVT, or even during startup, then the GNFB loop instantly wakes up. It dynamically turns the right number of main current source slices on or off to nudge VAES back into the safe zone.
And then it switches off again.
And then it disengages again. It's adaptive, only acts when needed. Very efficient. And importantly, this global loop runs really slowly, clocked below 10 kilohertz, so it uses hardly any power. And again, unlike older analog approaches with separate power-hungry comparators and bleed paths, this is all integrated, all digital, scalable, robust.
Okay. Current source, local feedback, global feedback. Is there a fourth part?
Yes, one more layer. Component 4, RO bleed strength randomization. Thinking bigger picture about security, adding randomness is almost always a good idea. It makes an attacker's job much harder.
So how does this add randomness?
Well, remember those RO bleed paths in the local feedback? Instead of just setting a fixed number of them to be active, this system can randomly switch which ones, or how many, are turned on at any given moment.
So the bleed itself becomes unpredictable.
Exactly. It injects a small amount of controlled current noise into the system. Think of it like adding a bit of random static. It makes it much harder for an attacker to separate the real key-dependent signal variations from this intentional random noise. It further scrambles the side channel information. And they optimized this too. They used a 41-stage RO design specifically chosen to minimize the extra chip area and power needed for this randomization. Smart design. Oh, and one more thing on the physical side. The DSC design also uses careful layout techniques. Local, lower-level metal routing and on-chip capacitors, called MOS caps. These help reduce EM leakage directly from the hardware itself.
So tackling EM leakage right at the source too.
Yes, another layer of physical defense. It's a really comprehensive approach tackling power, EM, stability, and adding randomness, all within a synthesizable digital framework.
Okay, so DSC on its own sounds incredibly effective. The numbers you mentioned earlier, like getting MTD up to potentially hundreds of millions, that's huge compared to the baseline.
It is, yeah. A massive improvement over previous synthesizable techniques.
But the researchers didn't stop there, did they? Mode 3 combined DSC with something else, TVTF.
That's right, time-varying transfer function. They wanted to see if they could push the security even further.
So what's the idea behind adding TVTF? Is it just more attenuation?
Not exactly attenuation in the same way DSC does it. TVTF adds a different kind of obfuscation. They work in the time domain. The idea is DSC flattens the signature. TVTF then takes that flattened signature and essentially shuffles it around in time, making it incredibly hard for an attacker to line things up and correlate events.
Shuffles it in time. How does that work?
What's really fascinating is how TVTF introduces this dynamic, almost chaotic element. Instead of having a fixed, predictable electrical path between the AES core's voltage and the main power supply, TVTF makes that path constantly change, randomly.
So the connection itself keeps shifting.
Exactly. Imagine trying to watch something happen, but every time you look, the order of events seems different, maybe delayed differently. It makes building a consistent picture over time, which is what attackers need, almost impossible. Their analysis models just break down.
Okay, what's the mechanism? How does it shuffle the connection?
It uses another clever synthesizable circuit. This time it's a 16-phase switched capacitor circuit.
Switched capacitor.
Yeah, picture a network of tiny capacitors on the chip. They're constantly being charged up and then discharged, but in a random, unpredictable sequence.
So it's like a constantly changing buffer, a moving target for the power flow.
That's a good way to think about it. The path the current takes isn't static. It's always shifting based on which capacitors are connected when. Any leakage signature gets smeared and jumbled up over time. It destroys the temporal patterns attackers rely on.
How is the shuffling controlled? How does it know which capacitors to switch when?
There's a lightweight digital controller managing it, and it uses something called a 16-bit Fibonacci linear feedback shift register, an LFSR.
LFSR, like a random number generator for circuit.
A pseudo-random number generator, yeah. Very efficient for hardware. The controller uses the LFSR's output to randomly decide which capacitors to charge and which to discharge at any moment. It keeps track using a couple of small memories.
And the key idea, the shuffling part.
The key insight is this: the capacitor that's actually supplying power to the AES core at one instant. It will then get recharged from the main supply at a different, randomly chosen time later on.
Ah, so the power draw you see on the main supply at time X isn't directly linked to what the AES core was doing at time X. It's been delayed and shuffled.
Precisely.
Yeah.
It decouples the external observation from the internal activity in the time domain. It's like taking that deck of cards, looking at one, then shuffling thoroughly before looking at the next. Makes tracking the sequence impossible.
And this is all digital too. No complex analog parts needed.
That's another big advantage. Some older switch capacitor ideas needed extra analog circuits, called equalizers, to smooth out voltage ripples they introduced. But this digital TVTF design inherently creates that time-obfuscated random transfer function between the AES voltage, VES, and the main supply, VDD, without needing an analog equalizer.
So fully synthesizable, lower power, less complex.
Exactly. Clean, elegant, digital-friendly, maximizes security while minimizing design hassle.
So DSC and TVTF together, it's like a double lock.
That's a perfect way to put it. DSC is working hard to make the footprint constant, to flatten the signal. Then TVTF comes along and actively shuffles the terrain so that even if any tiny residual footprints remain, they get scattered randomly in time, making them impossible to follow or correlate.
So the attacker sees what? Just noise.
Pretty much. The researchers' measurements show traces that are, yes, highly suppressed. The signal strength is tiny, but also incredibly obfuscated. Jumbled up. An attacker doesn't just see a faint signal. They see a faint, statistically meaningless mess that defies their standard analysis techniques. The synergy between DSC flattening and TVTF shuffling is incredibly powerful.
Okay, the theory sounds amazing. DSC flattens, TVTF shuffles. But the proof is in the pudding, right? How did it actually perform under attack? The real-world tests.
Absolutely. And the researchers were extremely rigorous here. They ran extensive tests on that 65-millimeter chip they built, comparing Mode 1, unprotected, against Mode 2, DSE only, and Mode 3, DSEC plus TVTF.
And they used proper attack methods, the kind real attackers use.
Yes, standard powerful attack models. Things like a Hamming distance attack, focusing on the later AES rounds, and correlational power analysis, CPA, plus correlational EM analysis, CEMA.
CPA and CEMA, looking for statistical links between the signals and the key.
Exactly. And they did this in both the time domain and the frequency domain, covering different ways attackers might look at the signals.
Comprehensive.
Very. They also use something called Test Vector Leakage Assessment, TVLA. It's a statistical method to actually quantify how much the information leakage has been reduced, going beyond just whether an attack succeeded or not.
So measuring the improvement statistically.
Right. This wasn't just a theoretical demo. It was a serious stress test against realistic attack scenarios.
Okay, let's hear the results. Mode 2, first DSAce alone. How did it do against power analysis?
The results are, frankly, staggering from the baseline. Unprotected AES. MTD was just 7,000 traces for power CPA.
7,000. Very leaky.
Extremely. Now switch on DSA mode 2. The MTD jumped to 820 million traces in the time domain.
820 million.
Million. And 380 million in the frequency domain.
Okay, wait. From 7,000 to, let's take the 820 million. That's more than 100,000 times improvement. No, hang on.
It's over 54,000 times improvement compared to the unprotected baseline.
54,000. Okay, that's incredible.
It fundamentally changes the game. An attack goes from feasible in minutes to requiring potentially years of data collection, if it's even possible. And importantly, compared to the previous best single synthesizable technique from other research, DSE showed more than a 38 times improvement.
So a huge leap even over the prior state-of-the-art for scalable solutions.
A very significant leap, yes.
All right, now for the double lock, mode 3, DSA plus TVTF. What happened then?
This is where it gets almost unbelievable. With both DSAC and TVTF active, the correct key byte could not be revealed, period.
Even after how many traces?
Even after 1.25 billion encryptions.
1.25 billion.
Billion with a B. And that held true for both time and frequency domain attacks. They simply couldn't break it with that amount of data.
That translates to what kind of improvement factor?
Compared to the unprotected AES baseline, it's over 178,000 times improvement.
Wow. So needing 1.25 billion attempts. That just makes the attack practically impossible, right?
Essentially, yes.
Yeah.
The sheer volume of data needed, the storage, the processing power, it becomes infeasible for almost any adversary. It moves from very hard to don't even bother trying for side channel attacks.
And you go out.
Standard.
Okay, that was power analysis. What about the electromagnetic attacks, EM leakage? Did DSE and TVTF work against that too?
A very similar story, which is great news, showing broad protection. Unprotected AES, the EM MTD was around 9,000 traces, also very vulnerable.
Right.
DSE alone, mode 2, it pushed the EM MTD up to 250 million traces.
A quarter of a billion.
Yep. That's over 27,000 times improvement compared to unprotected. And again, critically, it was over 25 times better than the previous best single synthesizable technique for EM protection.
So DSE is strong against both power and EM.
Definitely. And then mode 3, DSE plus TVTF against EM attacks.
Let me guess. Unbreakable.
Same result. The key could not be recovered, even with 1.25 billion EM measurements, time or frequency domain.
Which is an improvement factor of?
Over 138,000 times compared to the unprotected AES for EM. Just unprecedented resilience against EM side channels, too.
These numbers are just staggering. And the TVLA tests, the statistical ones, did they confirm this?
They did. TVLA showed roughly a 95,000 times improvement in leakage suppression for DSAC alone. And when DSA was combined with TDTF, an astonishing 290,000 times improvement compared to the unprotected AES.
290,000 times less leakage.
These are genuinely monumental gains. The data just shouts that the side channel information is being suppressed down to basically noise level, statistically invisible to an attacker.
Incredible results. But there's always a but, isn't there? What's the cost? Does all this security slow down the encryption, use way more power, take up loads more space on the chip?
That's the crucial practical question. And the beauty here is, first, there is zero performance overhead.
None. Encryption is just as fast.
Exactly as fast as the unprotected core. That's vital for real-world use. You don't sacrifice speed for security here.
Okay, that's huge. What about power and area?
There are overheads, yes. You're adding circuitry. For DSIEC alone, mode 2, it adds about 28% to the active chip area and uses about 33% more power.
Okay, noticeable, but maybe not crazy.
Right. When you add TVTF as well, mode 3, the overheads go up a bit more. Area increases to about 52% larger, and power consumption is about 50% higher than the unprotected core.
50% more power and area? Is that considered acceptable?
In a grand scheme of things, yes. Very reasonable. Even minimal, some would say. Why? Because you have to weigh it against the cost of a breach. For applications handling sensitive data finance, secure comms, critical systems, a breach could cost millions, billions, or even lives. Compared to that, a 50% increase in power, maybe slightly shorter battery life, or a slightly bigger chip. That's a trade-off most would take in a heartbeat for this level of security.
Especially security against over 1.25 billion traces.
Exactly. It's an incredibly good return on investment in terms of security achieved versus resources spent.
So how does this stack up overall compared to everything else out there? You mentioned a comparison table in the paper.
Yeah, looking at that comparison, this work really shines. It hits that 1.25 billion MTD mark, which is actually 25% higher than some previous combined strategies that also reached around the 1 billion level. So even better protection.
Okay.
But the absolute key differentiator, the thing we keep highlighting, is that it's fully synthesizable.
Which many other high protection methods weren't.
Correct. Many relied on analog bits, making them hard to scale. This work breaks that barrier. It delivers top-tier protection and the ease of implementation that comes with synthesizable digital design.
The best of both worlds, finally.
That's really what it represents. It's not just a small step. It feels like a paradigm shift, making truly robust physical security practical and scalable for the devices we'll all be relying on. #tag outro.
Wow, what an absolutely incredible deep dive that was. We've really seen how you can make something like AES 256 physically secure, not by changing the math, but by cleverly engineering how it interacts with power, how it emits signals right there on the hardware. This research delivers this synthesizable digital signature attenuation circuit DSRC, getting these unbelievable MTDs up to 820 million on its own. And then you add the time-varying transfer function, TVTF, and the key becomes basically impossible to find, even after 1.25 billion tries. And all of that with no speed penalty and what sounds like pretty reasonable overheads. Just amazing engineering.
From a broader viewpoint, yeah, this is a really significant step for secure hardware design.
Okay.
That focus on making it synthesizable, digital-friendly, that's key. It means these powerful defenses can actually be built into a huge range of devices, easily and affordably. Everything from tiny IoT sensors to massive data center hardware, critical infrastructure. It really hammers home the point that true security isn't just about the software or the algorithm. You have to secure every layer right down to the physical silicon. And, it does raise an interesting question for the future, doesn't it? As we get better and better at shutting down these known physical side channels, like power and EM, with techniques like DSE and TVTF, what will attackers think of next? What new, maybe even more subtle physical leakages might they try to exploit? And how do we stay ahead of that curve?
Always a cat and mouse game.
Always. We need to keep innovating, keep thinking like the attackers.
So what does this all mean for you listening right now in your daily life? Well, every single time you use encryption, your banking app, your smart speaker, secure messages, even just browsing secure websites, you're trusting that your secrets are staying secret. This deep dive is a powerful reminder that even if the software says secure, even if the math is perfect, the hardware underneath has to be just as watchful. Designed to prevent these physical leaks, it really makes you wonder, what other invisible footprints are our devices leaving behind? Things we haven't even thought about yet. But the good news, the hopeful message from research like this, is that with enough ingenuity, with brilliant engineering, we can make those footprints virtually disappear. We can secure our digital lives right down to that fundamental physical level. And in a world that's only getting more connected, that kind of fundamental security, that peace of mind, it's worth every single bit of effort.